Hey, welcome back. In the videos for this week, we're going to discuss some complexity classes and some graph problems that are in those complexity classes. In this video, we're going to focus on the complexity class P. P is the class of problems that can be solved in polynomial time in the size of the instance, whatever instance of the problem that you were given. And when I say polynomial time, I mean polynomial time using a deterministic Turing machine. So a classical computer. And earlier in this course, we've already seen some graph problems that are in the class P. For example, here's a simple one. Detecting whether a given graph G is triangle free. We can see that this one is in P because we can search through all triples of vertices in G and check whether there are edges between all of the vertices in each of those triples. And if none of those triples have edges between all of the vertices, then the graph will be triangle free. And if there's any triple that has edges between all of the vertices, then there's a triangle. So it's not triangle free. And earlier in the course, much earlier, back when we were talking about adjacency matrices, we discussed some algorithms for detecting whether a given graph G is connected, calculating the distance between pairs of vertices in G, and counting the number of walks of a given length, like 1, 2, or 3, between pairs of vertices in G. All of these problems we're able to solve using the adjacency matrix of G. And I claim the algorithms that we discussed to solve all of these using the adjacency matrix, all of those algorithms were polynomial time algorithms. So all of these problems in this fourth bullet are in P. And for one of those problems, the problem of connectivity, determining whether the given graph is connected or not, I leave this as a problem for you to think about. Why can we detect whether the given graph is connected in polynomial time in the size of the given graph? So this word up here, instance, this word can apply to many different kinds of problems. In the case of these problems here, our instance is the graph, the given graph. So here's another problem that we can ask about a graph, a connected graph specifically. Given some connected graph G, find a connected acyclic subgraph T of G, where the vertex set of T is equal to the vertex set of G. And this connected acyclic, that means it's a tree. And the special name of this kind of subgraph, a subgraph that is a tree which spans the whole vertex set, we call it a spanning subtree. And we're going to discuss two polynomial time algorithms for finding a spanning subtree in a given connected graph G. And polynomial time, again, this algorithm is polynomial time in the size of the instance, so the size of the graph. So when we have a graph, when we're talking about polynomial time in the size of the graph, we mean polynomial time in the order of the graph, the number of vertices. So let's talk about one algorithm for finding a spanning subtree. You'll notice with these two algorithms, you can think of one of them as an algorithm where we successively add vertices, and the other algorithm will be one where we successively add edges. This will be the vertex algorithm where we add the vertices, and we'll do the edge one second. So in the beginning of this algorithm, we just pick an arbitrary vertex in our connected graph G, and we mark it as part of T. T is the tree that we're building. So in the beginning, we're just starting with T as a single vertex with no edges. And then we have these two steps, we call them A and B, and we repeat them until every vertex in the graph G is in T. So step A, we choose an arbitrary vertex V in our tree T and U not in our tree T. And when I say in T and not in T, I mean currently. So V is currently in T, U is not currently in T. And we require that U and V are adjacent in G. Then step B, we add both U and the edge UV to the tree T. So before U was not in T, and of course the edge between U and V was not in T because U is not in T. And now both U and that edge are part of T. So T gained one vertex and one edge. And we can see why this is clearly a polynomial time algorithm in the size of G. So we'll suppose that G has order n, so the number of vertices in G is n. And we can see how long it takes us to perform the steps. So each time we perform these steps, we add a vertex to T and we add an edge to T. And since we only have a total of n vertices, we can only perform these steps at most n times, or else we would have too many vertices in T. We would run out of vertices in G to add to T. So these steps are only repeated at most n times. And so we'd like to get some upper bound on the running time of these steps. And so we need to see what running time upper bound can we get on step A in particular. Step A is the more difficult one. So for step A, we need to choose an arbitrary vertex V that's already in the tree T and U that's not already in the tree T, such that U and V are adjacent in G. So one way we could do this is we could list the edges of G. And we'll call these edges V1, V2. So those are two vertices in some edge. And we'll check whether or not V1 and V2 are in T. So we can just check for both of those vertices in each of the edges of G. So given any edge of G with some vertices V1 and V2 in it, we just check whether or not V1 is in T and whether or not V2 is in T. And based on that check, we can determine whether exactly one of them is in T, and that means the other one's not in T, and that gives us a valid vertex V and vertex U. And the fact that U and V are adjacent, that's taken care of by the fact that we are checking the edges of G. So the number of edges of G, the edge set of G, we know that that is big O of n squared in cardinality. It could be theta of n squared. It could be little o of n squared, but it's definitely big O of n squared. So that list has length big O of n squared. And then for each edge on that list, for each of these edges right here, V1, V2, we just check for the given V1, whether it's in T, and the given V2, whether it's in T. And that takes big O of n time. And I'm definitely not claiming that it takes theta of n time. I'm just claiming big O of n. So only an upper bound there. And an obvious way to see that is the cardinality of T is at most n. So we can just list through the elements of T and see whether they equal V1, any of them, just with a for loop. And same with V2. We can just do a for loop through the elements of T, see if any of them equals V2. So of course, this is a really dumb way to check if we have two vertices, V and T and U not in T, that are adjacent. It's a really dumb brute force way, but it doesn't matter if it's dumb. We're just trying to show that there is a polynomial time algorithm in the size of G to solve this problem, and this suffices. So each of the edges takes big O of n time to see whether it has one vertex in T and one vertex not in T. And there's big O of n squared edges, so big O of n squared times big O of n. And that's how we're getting right here, big O of n cubed. And we're getting big O of n cubed for each step. And we also have the step B. We didn't discuss this one yet. And step B, I will erase a little bit so we can read that. Okay. So for step B is just adding U and the edge UV to T. And that's already after we've found U and UV. So we found a U that's not in T and some V that is in T for which there is this edge UV. And so once we've found them, adding them to T, of course, takes little o of n cubed time. So it does not take theta of n cubed time. It takes little o of n cubed time. So strictly smaller than n cubed as n goes to infinity. So the limit of the runtime of that step B over n cubed goes to 0 as n goes to infinity. So the point is that step B is negligible compared to step A. And so we can say that step A and step B together, so step A plus step B, is big O of n cubed time. Even if step B was big O of n cubed, like step A, we would still have the sum is big O of n cubed, but step B is little o of n cubed. And since we have a total of n iterations of these steps, so we repeat these steps at most n times. So the runtime in total, n times big O of n cubed, that's an upper bound on it. So we can say the runtime is big O of n to the fourth. So if we're trying to get an upper bound on the runtime in terms of the order of the graph for some polynomial time algorithm, we can analyze it like this. So we can break down the steps. We can look at the runtime for steps of the algorithm, and then we can multiply or add certain runtimes together. So for this algorithm, we were multiplying. But if this algorithm had another component that we added onto it, then we would add the runtime of that component. So we're multiplying here because we were basically doing a loop. We were repeating these steps until we ran out of vertices in our graph to add to T. So let's look at another problem. And I lied, it's the same problem, but I mentioned another algorithm. So spanning subtree again. We're just trying to find that spanning subtree for our graph G. And I said before that we would look at two algorithms for it. So we saw before on the previous slide an algorithm for finding a spanning subtree where we add a vertex at a time. So that's like the vertex adding algorithm. And now for the second one, we're going to see an algorithm where we add an edge at a time. And this one's very different because the first algorithm, our tree T that we were updating, it started connected and it stayed connected the whole time, but it grew in order. So the number of vertices in the tree grew. Now, for this algorithm, we're not going to start with a tree. It'll only become a tree at the end. It's going to start disconnected, and it's going to start with all the vertices too. So we're not going to be adding vertices. We'll have all of them from the beginning. We'll only be adding edges. And it'll still give us a way to find a spanning subtree T in polynomial time. So here's this edge adding algorithm. So our starting state for this algorithm, we start with T, and it is a disjoint union of trees of order 1. So in other words, T is a bunch of singleton vertices, and it's all of the vertices in G. So I should probably specify that. So all of the vertices in G, we start with the T, but none of the edges. So everything is just singletons. It's a big independent set at the beginning. And then we do this again and again. As long as the current T has at least two connected components, add a single edge from the graph G between the connected components. And I claim that that gives us a tree at the end, because this must terminate at some point. So the number of connected components at the beginning, so the initial number, is equal to the cardinality of the vertex set of G, which we called n on the other slide. Might as well call it n here. And each step, when we add this single edge, that is an edge from the graph G. So we can't just make up some edges. We can only use edges that are in G. But when we add that single edge between the two connected components, those connected components are both trees. So at any step of this algorithm, both of those connected components are trees. And when we add that edge, they remain trees, because you take two trees, you add an edge between them, it stays a tree. But in addition to that, when we add that edge between the connected components, each of these steps, each time it decreases the number of connected components. It decreases it by 1 specifically, although it's not important really to say that because I'm just mentioning this for the fact that we can say that these steps right here happen at most n times because the number of connected components has to decrease each time, and it starts at n. So each time we add these edges between different connected components, our set of connected components remains a disjoint union of trees, and we lose a connected component each time. So our number of connected components goes down each time. So we know this algorithm terminates, and it terminates with a tree. And that tree has all the vertices in our graph G because at all steps, this graph T always had all the vertices of G. But I'll leave this problem to you. So we did an analysis on the last slide, and we saw that the other algorithm for finding the spanning subtree, the algorithm where we add vertices instead of adding edges. So when we analyzed that on the other slide, we saw that was a polynomial time algorithm. And we even found an upper bound for it in terms of the order and of our graph G. So this problem is, can you explain why the algorithm that we discussed here is also a polynomial time algorithm in the order of the graph G? And it might be helpful to use the fact that you can detect whether a graph is connected in polynomial time. So as long as there exists at least 2 connected components of the tree, and I shouldn't call it the tree, I should call it T because it only becomes the tree at the end. So see if you can determine why the algorithm we discussed is a polynomial time algorithm. You don't necessarily need to find an upper bound in the order of the graph G, although you're welcome to. Just explain in a reasonably logical way why each of the steps can be done in polynomial time. So you don't have to necessarily put all the details, but give enough details that it would be convincing to most people. So let's look at another problem that we can solve in polynomial time. We'll just look at a single algorithm for this one. And then we'll see another problem that's kind of a similar type of problem to this. So for this one, given a connected graph G, which has vertex set V and edge set E, find the radius and a center of this graph G. So let's quickly review what that means. So the radius of the graph G is the minimum value over the vertices V in the vertex set. So the minimum over all these vertices of the maximum value over vertices U in our vertex set of the distance between U and V. So the radius is the smallest that we can make the maximum distance. And it's the smallest over all vertices. So it's possible that we might just have one vertex V here that attains this minimum, or we might have multiple. Any vertex V that attains that minimum is called the center. And it's called a center, so it's not necessarily the, because we could have multiple centers. So let's look at some examples. And we can look at another example here. So this one over here, the radius is 1. And the center is this vertex right here. So we can look at, for each vertex, the maximum distance to all the other vertices. And each of the vertices, we can write that maximum on the vertex. So this one, the maximum distance to any of the others is 1. This one, the maximum distance to any of the others is 2. Same with this one's 2. So the distance from any of these leaves, it's 1 to the center, but it's 2 to any of the other leaves. So all these have 2. So all the vertices except for that one in the center have this maximum equal to 2. So that center one, we have 1 right there. Let me write that 1 a little more clearly. So that's a special one because it's less than all the others. And so when we minimize over all the vertices, when we minimize this max, and again, we've drawn this max on each of the vertices. So all of these are the maxes. And when we minimize those maxes, only one of them is 1. So the minimum value was 1. That was our radius. And there was only one center. That was our center, right in the center. Now this one is different over here. So let's look at this one. So we can take each of these vertices and we can see what's their maximum distance to any of the other vertices. So this one here, maximum distance is 3 because this is the one that's farthest from. Same with this, 3 here, 3 here, 3 here. And then this center one right here. So this graph, it's a spider. So the body vertex right here. This body vertex, its max distance is 2. So the same vertex, this one over here, that's the one that's distance 2 to it. Now this one right here is weird. Its max distance is also 2. Since its max distance to all these leaves out here, besides this leaf on its own leg. And this one, of course, is max distance 3, like all those other leaves. So in this one, we have radius 2. And we have 2 centers here. So there's our 2 centers. So the problem here is to find the radius and find a center. And one way we can do this is we can take all the vertices of our graph, so all the vertices in V, and we can make a list of their distance to all the other vertices. And I'm just gonna underline, our graph is connected here, so every vertex has some distance to every other vertex. And we can compute all these distances to the other vertices for each of our vertices in polynomial time, like I mentioned earlier, using the adjacency matrix. So using the adjacency matrix of G, using powers of that matrix, we can determine the distance between every pair of vertices in our graph. And then for each vertex, we can find what's the maximum distance on its list. So each of the vertices, we have a list of its distances to all the other vertices, and we just pick the maximum distance for each vertex V, and we'll call that M of V. And the radius is just the minimum value of M of V over all the vertices, little v, in the vertex set. And in order to find a center, we just need to output any vertex which gives that minimum. So that was a polynomial time algorithm to find the radius and a center. And now here's a related problem which we discussed before, and I'll leave it to you to find a polynomial time algorithm for this one. So given some graph G, find a polynomial time algorithm in the size of G for computing the diameter of G. And the diameter of G, what is the diameter again? it is just the maximum distance between any two vertices in G. So you can assume for this problem, just like on the last slide, that G is connected. Although you don't have to assume it's connected here. So if you're given a disconnected graph G, you can run a routine at the beginning of your algorithm to determine whether or not G is connected. And if your algorithm says that G is disconnected, then for this problem, outputting the diameter for a disconnected graph, you could just say infinity for disconnected. But if you would like to assume that G is connected, that's fine, because I already discussed what to do for when it's disconnected. So you may assume it's connected. And so find a polynomial time algorithm in the size of the graph G for computing the diameter. And the diameter, we already saw some examples on the previous slide, how to find the radius. So the diameter here, we can use the same numbers we had before. So we can look at, for each vertex, what's its maximum distance to any of the others. And we can just look at all those numbers and take the maximum one. So over here, the maximum ones are all 2. So we can just take one of those 2's, and that's the diameter. So the maximum distance between any two vertices in that one is 2. And over here, there's a bunch of occurrences of the maximum, which is 3. So I'll leave that problem for you to think about. And you can use a similar method to the one that we talked about on the other slide. And in the next video, we will discuss the complexity class NP and some problems in that class. Thanks for watching.